In this video, we're going to take a look at some chemical reactions of amides. Now, like amines, we saw that amides could have primary, secondary, and tertiary structures. And with amines, we had the same basic chemical reaction for making all of those. And the same thing happens with amides. So if we remember this one chemical reaction, we'll remember then how to make primary, secondary, and tertiary amides. So we're going to start out with making a primary amide. So I'll start out here with a carboxylic acid. This here is our methanoic acid, carboxylic acid, and I'm going to react that with ammonia. Now ammonia has this structure here, nitrogen, like this, with our hydrogens, and that lone pair. Okay, so there's ammonia. And we will react that then with heat. And then with this, what's going to end up happening is you might look at this and go, oh my gosh, wait a minute, I've seen this before somewhere. I've seen this before, where we could perhaps maybe remove a hydroxyl group here and a hydrogen there. What would happen? Well, we'll end up with water over here. Water, and then we'll bring this amine group and attach it onto the carboxylic acid. Like this, okay? And so now this becomes a primary amide. And the name for this one would be methanamide. Okay, so let's take that. Let's take our primary amide over there. Excuse me. Let's make a secondary amide. So to make a secondary amide, we're going to start out with our carboxylic acid here again. And we will react this with then a primary amine. So nitrogen, hydrogen, and then we would have R on here like this. Okay, and that could be 1 carbon, 2 carbons, or whatever. Okay, so this right here is going to be a primary amine, and same reaction conditions here. We just add some heat to it like this, and like we saw before, we're going to remove water like this, so we end up with water like that, and then we're going to bring this primary amine over and attach it onto our carboxylic acid. So C, double bond O, hydrogen, nitrogen, R, H like this, and then we end up with a secondary amide. Secondary amide. And then let's bring this over here again, and let's do the same thing. And we're going to make a tertiary amide. So I'll get my carboxylic acid here. Hydrogen, okay, carboxylic acid. And then I'm going to attach it now to, or I'm going to react it with a secondary amine. So nitrogen, like this. I'll go R and R like this, and then hydrogen like that. This is a secondary amine. So maybe I should label this here. Here's ammonia. Ammonia, and then here is a primary amine, and here is a secondary amine. And then this right here is a carboxylic acid. carboxylic acid. Okay, and then my reaction conditions on this, if I had to guess, would be the same. It'd be heat. Okay, add some heat to that there, and then we're going to remove some water like this. Take that off of there. We'll end up with some water. Okay, and now we're going to end up with our tertiary amide. So we'll go carbonyl group, hydrogen, nitrogen, and like that. And then this here is going to be my tertiary amide. Now the next reaction we're going to take a look at is the hydrolysis of an amide. Hydro means water, lysis means to break apart. So let's start out with our amide. So we'll start out with my carbonyl group like this. Okay, and we'll go nitrogen like this, and we'll go like that. Okay, so here is a secondary amide, and I'm going to react this with water. Like that, reacting it with water. And to make this happen, I'd have to add some heat to it. This triangle above the arrow there just means heat, just adding some heat to it. Okay, so when I do this, I'm going to break my water molecule apart. So my water molecule here gets broken apart like that, and the hydrogen's going to go one place, and then the hydroxyl group will go someplace else. And we've kind of seen this in reverse fashion, I suppose, when we looked at how we made amides in amidification. So we're going to take this hydroxyl group, bring it over here, and we're going to turn this back into a carboxylic acid. And so here we'll have our R like this, our carbonyl group like that. There. Okay, there's my OH. My OH is here. Okay, now I've made my carboxylic acid. And what else do I end up with then over here is I'm going to have my amine group over here. So I'm going to add this hydrogen over here, and I'll end up with an amine. So we'll end up here with NH2R like that. So an amine. All right. So this right here is hydrolysis. Now we could do this under acidic or basic conditions, and we'll end up with something a little bit different. So if I start out then with the same thing here, same thing here. I'll go here, R like this, and then carbonyl, and then nitrogen like this, and then like that. Okay. And then I'm going to add water to this, like that. And then I'm going to add some hydrochloric acid, like this. Okay, and then we'll put some heat in there. Okay, well, now what's going to happen? What are our products going to be here? Well, we're going to end up splitting our water apart here. We'll split our water apart there like that, and we're going to split apart our hydrochloric acid as well. Okay, so now in our products here, we're going to end up with our carboxylic acid. So we'll go R like this, carbonyl. Okay, we've seen this before, right? You've seen that before. And then we're going to end up with an amine salt over on the other side here. So over here, we'll end up with our amine salt. So this will be NH3R like this, okay? And this has a plus charge like that. So we've taken the hydrogen, we've attached it over there. That's going to make it an amine salt. And then we've got the chloride here. So we'll make the chloride like that there, okay? So that gives us an amine salt. An amine salt. Okay. And let's see here, NH3, okay, all right. And then what happens if we do this under basic conditions? Okay, so if we did this whole thing under basic conditions, let me just change this here. I'll change that to sodium hydroxide, NaOH, like this here, sodium hydroxide, all right? So then what are my products going to be over here? Well, this here is going to be a little bit different, okay? A little bit different here now. Okay, so we're going to split our sodium hydroxide apart, like this here. Okay, our sodium then is going to come over here, and we might have seen this before, where I had our carboxylic acid salts. So we end up with Na here, right? So this becomes sodium, say methanoate. Okay, this is our carboxylic acid salt. And then also then with this is we end up then with our amine. Okay, and so our amine ends up being our, let's see here, NH2R, like this. And I think what we have left over then is just water. It's just water being left over. Okay, so this here would be an amine. And a carboxylic acid salt. Okay. How about that? All right, so let's try to find a real-world example where all of this comes into place. So one of my favorite stories was back in World War II, the United States, if you remember your history, got into this little tuffle with this country over on the other side of the Pacific called Japan. And Japan was one of the primary sources of making silk, and so was China. And if you wanted to get silk back in World War II, you had to ask the Japanese, and they weren't going to sell it to us. And you could ask the Chinese, but they were overrun by the Japanese. So again, you'd have to ask the Japanese, and they weren't going to sell it to us. So why would we need silk, right? You think, oh, well, there's a war going on. Maybe we just won't have silk stockings and scarves and such. And, yeah, okay, fine, we'll make that sacrifice. But back then, they used silk for something different. They used it for making parachutes. And when you're at war and you have the paratroopers, like the 101st Airborne and the 82nd Airborne, you don't want to jump out of an airplane without your silk parachute. And so we needed a substitute for silk. And so some chemists got together and said, well, all right, let's figure something out here. So what they did is they started out with two molecules here. So let's start with the first one here. This one is your carboxylic acid here. And then here I'm going to go CH2, and then there's 4 of those because I'm too lazy to write the whole thing out, like this here, and then OH. Okay, so here's my dicarboxylic acid. And there's 1, 2, plus 4 carbons in here, okay? So this becomes hexane dioic acid, okay? Hexane dioic acid, all right, good, okay. And then another molecule here is going to be your nitrogen like this, and hydrogen like that, and then we're going to go CH2, and we're going to go 6 of those here like this, okay, and then nitrogen, hydrogen, and like this, okay. Now this one here becomes there's 6 carbons here, and then we have an amine on either end, okay? And so this becomes 1,6, okay, hexane, hex, and diamine, hexane diamine. All right, now we can look at these two molecules, and we're probably getting good at this, where we recognize, okay, wait a minute, I know what you're doing here. Well, I see an OH here and a hydrogen there. I bet we can combine those together, right? We could link these two molecules together, and you'd be right. We just remove water. Hydrolysis reaction here. And if we had a bunch of these, okay, then we could just string them together in a long chain, right? So you see this amine group over here can attach to another carboxylic acid group over here, and you could just keep on repeating this thing. And you could. And so what you end up doing is you create this big, long polymer. And this big, long polymer is a polyamide. Okay, so this becomes a polyamide. And this polyamide becomes what's known as 6,6 nylon. Now it's called 6,6 nylon because there's 6 carbons here, 6 carbons here, right? So there's 6 carbons in the carboxylic acid. There's 6 carbons over here in the amine. And so this 6,6 nylon then was used as a replacement for silk. And so nylon was invented in part to replace silk back in World War II. So now you could jump out of perfectly good airplanes without your silk parachutes, right? So that's kind of cool. That's kind of neat. And then another one here. I'll show you a more modern example of an amide. And this one here, it's going to tax my artistic skills a little bit here. But if I take and make a benzene ring like this, nitrogen like this, bond like that, and we'll go like this, okay, like that, okay, and then double bond O like this, and then over here we have nitrogen and hydrogen like this, okay, and like that. So this molecule right here is a fairly stable molecule, and what we're going to do is we're going to make another polymer out of it, and that is over this side here we've got a carboxylic acid, and over here we have an amine. And if we link repeating units of this together, where we have the amine attaching onto the carboxylic acid like this, we end up then with another polyamide. And this one happens to be Kevlar. And Kevlar is the material, the synthetic material that is used in the military. It started out Kevlar helmets and bulletproof vests, as it was really good at stopping bullets. And so Kevlar is a polyamide. A little bit of chemistry there for you, real world application.